Hello there, and welcome to the Sleepy Science channel. Tonight we will be venturing into the mysterious and beautiful realm of quantum physics, a place where particles dance between existence and non-existence, where reality itself seems to shimmer with uncertainty, and where the very act of observation changes what we see. This is the world of the infinitely small, where the rules we take for granted dissolve into something far stranger and more wonderful. The quantum realm is both invisible and everywhere, governing the behavior of every atom in your body, every photon of light that reaches your eyes. If you enjoy these quiet explorations, I invite you to like and subscribe, or share a simple thought down in the comments. It helps others find their way here, too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the gentle mysteries of the quantum world to carry you. Let's begin. The quantum world. Everything around you is made of particles far too small to see. The chair beneath you, the air you breathe, the screen before your eyes. All of it is composed of atoms, and atoms themselves are made of even tinier pieces: protons, neutrons, and electrons. These particles are so small that billions of them could fit on the head of a pin. Yet within their microscopic dance lies the foundation of everything we know. At this scale, matter behaves in ways that defy our everyday experience. Particles can exist in multiple places at once. They can tunnel through barriers. They can become entangled across vast distances, responding to each other instantaneously. The quantum world is not just small, it is fundamentally different, operating by rules that seem impossible until you look closely enough to see them in action. Quantum mechanics emerged from mysteries that puzzled scientists for decades. In the late 1800s and early 1900s, physicists noticed strange behaviors in light and matter that classical physics could not explain. Light sometimes behaved like a wave, spreading and interfering with itself. Other times, it acted like a particle, arriving in discrete packets. Electrons orbiting atoms did not crash into the nucleus, as they should have, according to older theories. Instead, they remained stable, occupying specific energy levels that seemed to defy logic. These puzzles led to a revolution in understanding. Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others began constructing a new framework. What emerged was quantum mechanics, a theory that described the behavior of nature at its smallest scales. It was strange, counterintuitive, and profoundly successful. Today, quantum mechanics underpins much of modern technology, from the transistors in computers to the lasers in fiber optic cables. At the quantum scale, particles do not have definite positions until measured. Imagine holding a coin in your hand. You know exactly where it is. But in the quantum world, particles exist in what physicists call a superposition. Before you observe them, they occupy multiple positions simultaneously, each with a certain probability. It is only when you measure their location that they collapse into one specific place. This is not because our instruments are imprecise. It is a fundamental property of quantum systems. The particle genuinely exists in all those places at once, spread out like a wave of possibility. Erwin Schrödinger developed an equation to describe this behavior, showing how the probability wave evolves over time. The equation does not tell you where a particle is. It tells you where it might be, and with what likelihood. This probabilistic nature troubled many early physicists. Even Einstein, who helped birth quantum mechanics, struggled with its implications, famously remarking that God does not play dice with the universe. The act of observation fundamentally alters quantum systems. In classical physics, you can measure something without changing it. You can look at a tree without affecting the tree itself. But in quantum mechanics, observation is not passive. When you measure a particle's position, you disturb its momentum. When you measure its momentum, you blur its position. This is not a limitation of technology, but a feature of reality. The observer and the observed are intertwined in ways that cannot be separated. This principle, known as the observer effect, reveals that the universe at its smallest scales is participatory. Reality does not exist independently of measurement. It emerges through interaction. To observe is to become part of the system, shaping what you see by the very act of looking. This strange interdependence between measurement and reality continues to inspire philosophical reflection and scientific inquiry. Heisenberg's uncertainty principle places limits on what can be known. Werner Heisenberg discovered that there are fundamental limits to precision in the quantum world. You cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you measure one, the less precisely you can know the other. This is not about the quality of instruments. It is woven into the fabric of nature. The uncertainty principle arises from the wave-like properties of particles. A wave that is perfectly localized, occupying a single point, has an infinite range of possible momenta. Conversely, a wave with a precise momentum spreads out over space. The two properties are inversely related, creating an unavoidable trade-off. This principle has profound implications. It means there are questions the universe itself cannot answer. There are states of being that cannot exist. Certainty, at the quantum scale, is an illusion. Particles can tunnel through barriers they should not be able to cross. Imagine throwing a ball at a wall. If you do not throw it hard enough, it bounces back. But, in the quantum world, particles can pass through barriers, even when they lack the energy to do so classically. This phenomenon is called quantum tunneling. It occurs because particles are not just particles. They are also waves, and waves can leak through obstacles. The probability of a particle being on the other side of a barrier is never exactly zero. Given enough attempts, it will eventually appear there. Quantum tunneling is not just theoretical. It is happening all the time. It allows nuclear fusion to occur in the sun, where protons tunnel through the electromagnetic barrier that repels them, enabling them to merge and release energy. It is also the basis for technologies like tunnel diodes and scanning tunneling microscopes. The universe, it seems, allows for shortcuts through walls that look impenetrable. Quantum entanglement connects particles across any distance. When two particles become entangled, they share a quantum state. Measuring one particle instantly determines the state of the other, no matter how far apart they are. This connection is not mediated by signals traveling between them. It is instantaneous. Einstein called this spooky action at a distance and remained skeptical of it throughout his life. Yet, experiments have repeatedly confirmed that entanglement is real. If you measure the spin of one entangled electron and find it pointing up, the other electron's spin will point down, even if it is on the other side of the galaxy. The correlation is perfect and immediate. Entanglement does not allow faster-than-light communication because the results appear random until compared. But it reveals that the quantum world is deeply non-local. Particles that have interacted once remain connected in ways that transcend space. No information travels faster than light, even in entanglement. Quantum entanglement might seem to violate Einstein's theory of relativity, which states that nothing can travel faster than light. But entanglement does not transmit information in the usual sense. When you measure one entangled particle, you instantly know the state of its partner. However, the outcome of your measurement appears random. You cannot control it. Only when you compare results with someone observing the other particle do you see the correlation. That comparison requires classical communication, which is limited by the speed of light. So while the connection is instantaneous, The information about the connection is not. This preserves causality and the structure of space-time. The universe maintains consistency even as it reveals strange connections beneath the surface. Entanglement shows us that locality and reality as we perceive them may be approximations of something deeper and more interconnected. The double-slit experiment reveals the dual nature of particles and waves. One of the most famous experiments in quantum mechanics is deceptively simple. Shine light through two narrow slits onto a screen behind them. Instead of two bright lines, you see an interference pattern, bands of light and dark. This happens because light behaves as a wave, with peaks and troughs that combine and cancel each other. But here is the mystery. If you send one photon at a time through the slits, the interference pattern still builds up over time. Each photon seems to interfere with itself, as though it passes through both slits simultaneously. Yet, if you place a detector at the slits to see which one the photon goes through, the interference pattern vanishes. The photon behaves like a particle, going through one slit or the other. The act of measurement changes the outcome. This experiment has been repeated with electrons, atoms, and even large molecules, always with the same result. It suggests that particles exist in a superposition of possibilities until observed. Wave-particle duality means light and matter are both and neither. For centuries, scientists debated whether light was a wave or a stream of particles. Quantum mechanics revealed that the question was flawed. Light is both and neither. It exhibits wave-like behavior in some experiments and particle-like behavior in others. The same is true for matter. Electrons, atoms, and even molecules display interference patterns like waves, yet they arrive at detectors as discrete particles. This duality is not a contradiction, but a deeper truth. At the quantum level, entities are neither purely waves nor purely particles. They are something more fundamental, quantum objects that manifest different aspects depending on how they are observed. The universe does not fit into the categories we have created. It exceeds them, showing us that reality is richer and stranger than language can easily capture. Every particle in the universe has a wavelength associated with it. Louis de Broglie proposed that if light, traditionally thought of as a wave, could behave like particles, then perhaps particles could behave like waves. He was right. Every particle has an associated wavelength, determined by its momentum. For large objects, this wavelength is incredibly tiny, far too small to observe. But for electrons and other subatomic particles, the wavelength is significant, leading to observable wave-like behavior. This insight unified the behavior of light and matter under a single framework. It explained why electrons in atoms occupy discrete energy levels. They form standing waves around the nucleus, and only certain wavelengths fit. De Broglie's matter waves transformed quantum mechanics, showing that wave-particle duality was not limited to light. It is a universal property of nature. Quantum superposition allows particles to be in multiple states at once. Before measurement, a quantum particle does not occupy a single definite state. It exists in a superposition, a combination of all possible states simultaneously. An electron can be in multiple locations, spinning in multiple directions, carrying different energies all at the same time. This is not ignorance on our part. The particle genuinely inhabits all these states. The superposition is described by a wave function, a mathematical object that encodes probabilities for each outcome. When a measurement occurs, the wave function collapses, and the particle settles into one definite state. The collapse is instantaneous and seems to happen without a clear physical mechanism. a phenomenon that remains one of quantum mechanics' deepest mysteries. Superposition is what allows quantum computers to process vast numbers of possibilities at once, holding information in ways classical bits cannot. Schrödinger's cat illustrates the strangeness of quantum superposition. To highlight the absurdity of applying quantum rules to everyday objects, Erwin Schrödinger devised a thought experiment. Imagine a cat in a sealed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers, breaking the vial and killing the cat. Quantum mechanics says that, until observed, the atom exists in a superposition of decayed and not decayed states. This means the cat is also in a superposition, simultaneously alive and dead. Of course, when you open the box, you find the cat in one state or the other, not both. Schrödinger's point was to show how strange it is to extend quantum superposition to macroscopic systems. The experiment raises deep questions about measurement, consciousness, and the boundary between the quantum and classical worlds. It remains a touchstone for debates about the interpretation of quantum mechanics. The collapse of the wave function remains mysterious. When a quantum system is measured, its wave function collapses from a superposition of states into a single outcome. But what causes this collapse? The equations of quantum mechanics describe how the wave function evolves smoothly over time, yet they do not account for the sudden change during measurement. Some interpretations suggest that collapse is a real physical process triggered by observation. Others propose that the wave function never truly collapses. Instead, all outcomes occur in separate branches of reality. Still others argue that collapse is an illusion arising from the interaction between quantum systems and their environments. Despite nearly a century of study, the collapse of the wave function remains one of the most debated aspects of quantum theory. It touches on the nature of reality, the role of the observer, and the limits of what can be known. Many worlds' interpretation suggests all outcomes happen in parallel universes. One way to resolve the measurement problem is to take the wave function literally. In the many worlds interpretation, when a quantum measurement occurs, the universe splits into multiple branches. In one branch, you observe one outcome. In another, you observe a different outcome. Each possibility is realized somewhere. There is no collapse. The wave function continues evolving, encompassing all outcomes across a vast multiverse. This interpretation eliminates the need for a special measurement process. It treats all interactions equally. However, it comes with a staggering implication. Every quantum event spawns countless parallel universes. You exist in countless versions, each experiencing different outcomes. The interpretation is mathematically elegant, but philosophically challenging. It raises questions about identity, probability, and the nature of existence itself. The Copenhagen interpretation emphasizes the role of observation. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, was the first widely accepted framework for understanding quantum mechanics. It holds that the wave function represents our knowledge of a system, not necessarily an objective reality. Until measured, a particle does not have definite properties. It exists in a state of potential. Measurement collapses the wave function, bringing definite properties into being. The interpretation places the observer at the center of quantum mechanics. Reality, in some sense, is created through the act of observation. This view troubled many physicists, including Einstein, who believed in an objective reality independent of observers. Despite debates, the Copenhagen interpretation remains influential, shaping how quantum mechanics is taught and applied. It emphasizes the limits of what can be known and the active role of measurement in shaping outcomes. Quantum decoherence explains why we do not see superpositions in daily life. If particles can exist in superpositions, why do we never see a chair in two places at once? The answer lies in quantum decoherence. When a quantum system interacts with its environment, the delicate superposition states become entangled with countless particles in the surroundings. This interaction effectively destroys the coherence of the superposition, causing the system to behave classically. The process happens incredibly quickly for macroscopic objects, almost instantaneously. Decoherence explains why quantum effects are confined to isolated, microscopic systems. It does not solve the measurement problem entirely, but it clarifies why we experience a definite, classical world. The boundary between quantum and classical is not sharp. It is a matter of degree, determined by how much a system interacts with its environment. Quantum mechanics is one of the most successful theories in history. Despite its strangeness, quantum mechanics has been tested extensively and has never failed. It predicts the behavior of atoms, molecules, and subatomic particles with extraordinary precision. Technologies like semiconductors, lasers, and magnetic resonance imaging rely on quantum principles. The theory explains the stability of atoms, the properties of materials, and the interactions of light and matter. It has led to discoveries like the transistor, the foundation of modern computing, and the development of quantum cryptography, which promises unbreakable encryption. Quantum mechanics is not just abstract theory. It is the most empirically verified framework in physics. Its success suggests that, however strange it may seem, it captures something true and fundamental about the nature of reality. Photons are particles of light with no mass. Light, as we experience it, is composed of countless photons. Each photon is a quantum of electromagnetic energy, a discrete packet that travels at the speed of light. Despite carrying energy and momentum, photons have no rest mass. If they did, they could not move at light speed. This masslessness has profound consequences. It means photons are never at rest. They exist only in motion, forever racing through space at the maximum speed allowed by the universe. Photons are emitted when charged particles, like electrons, change energy levels. They can be absorbed by other particles, transferring their energy. Though individual photons are invisible and intangible, their collective behavior creates the light that illuminates the world. Every color you see, every ray of sunlight, every star's glow is the work of photons streaming endlessly through space. Photons can be entangled, creating perfectly correlated pairs. When two photons are created together in certain processes, they can become entangled, sharing a single quantum state. If you measure the polarization of one photon and find it vertical, the other will be horizontal, or vice versa, instantly. This perfect correlation holds regardless of the distance between them. Entangled photons have been used in experiments testing the foundations of quantum mechanics, consistently confirming its predictions. They are also the basis for emerging technologies like quantum cryptography, where entanglement ensures secure communication. Any attempt to intercept or measure the photons disrupts their entangled state, revealing the intrusion. These correlated pairs of light illustrate how deeply interconnected the quantum world is, binding particles together in ways that transcend the limitations of space. The photoelectric effect revealed the particle nature of light. In the late 1800s, scientists observed that shining light on certain metals caused them to emit electrons. Classical wave theory predicted that brighter light should release electrons with more energy. Instead, experiments showed that only light above a certain frequency could eject electrons, regardless of brightness. Brighter light released more electrons, but not more energetic ones. Albert Einstein explained this in 1905 by proposing that light is made of particles, later called photons. Each photon carries a specific amount of energy determined by its frequency. Only photons with enough energy can knock electrons free. This work earned Einstein the Nobel Prize and provided crucial evidence for the quantum nature of light. The photoelectric effect is now used in devices like solar panels and digital cameras, converting light into electrical signals. Electrons are fundamental particles with negative charge. Electrons are one of the building blocks of atoms, orbiting the nucleus in clouds of probability. They carry a negative electric charge and have a tiny mass, about 1/1800th that of a proton. Despite their small size, electrons are not made of anything smaller. They are fundamental particles, indivisible as far as current physics can determine. Electrons govern chemistry. The way atoms bond, the structure of molecules, and the properties of materials all depend on how electrons arrange themselves. They also carry electric current, flowing through wires to power devices. In quantum mechanics, electrons exhibit wave-like behavior, forming standing wave patterns around atomic nuclei. These patterns determine the energy levels and orbitals we learn about in chemistry. The electron is small, but its influence is vast, shaping the physical world at every scale. Electrons exist in discrete energy levels within atoms. When electrons orbit an atomic nucleus, they cannot occupy just any energy. Instead, they are confined to specific levels, like rungs on a ladder. To move between levels, an electron must absorb or emit a precise amount of energy, often in the form of a photon. This quantization of energy was one of the first clues that the atomic world operates by different rules. Niels Bohr proposed a model where electrons occupy fixed orbits, each with a defined energy. While later quantum mechanics refined this picture, replacing orbits with probability clouds, the concept of discrete energy levels remains central. These levels explain why atoms emit and absorb light at specific wavelengths, creating the unique spectral lines that identify elements. The discrete nature of energy in atoms is a direct consequence of the wave-like behavior of electrons, which can only form stable patterns at certain energies. Quantum tunneling allows electrons to pass through barriers instantly. Electrons sometimes cross barriers they do not have enough energy to surmount. This is quantum tunneling, a phenomenon with no classical analog. In the quantum view, an electron is described by a wave function that extends beyond the barrier. Even if the probability is small, there is always a chance the electron will be found on the other side. This effect is essential for many processes. It enables alpha decay in radioactive nuclei, where particles escape the nuclear force. It allows electrons to jump between electrodes in certain electronic components. It even plays a role in the fusion reactions that power stars, helping protons overcome their mutual repulsion. Tunneling shows that the boundaries we perceive as solid are, at the quantum level, porous and uncertain. Quantum spin is an intrinsic form of angular momentum. Every electron has a property called spin, but it is not spinning in the way a top spins. Spin is an intrinsic quantum property, a form of angular momentum that particles possess inherently. Electrons can have spin up or spin down, corresponding to two possible orientations. Despite its name, spin does not involve actual rotation. It is a purely quantum mechanical phenomenon with no classical counterpart. Spin has profound implications. It determines how particles interact with magnetic fields, leading to phenomena like magnetism in materials. It also governs the Pauli exclusion principle, which states that no two electrons in an atom can occupy the same quantum state. This principle is why matter has structure and why the periodic table takes its form. Spin is fundamental to the identity of particles and the behavior of matter. Fermions and bosons are the two types of particles. All particles in the universe fall into two categories based on their spin. Fermions have half-integer spin and obey the Pauli exclusion principle. Electrons, protons, and neutrons are fermions. No two fermions can occupy the same quantum state, which is why electrons fill up energy levels in atoms one by one. Bosons have integer spin and do not obey the exclusion principle. Photons are bosons, as are the particles that carry the other fundamental forces. Multiple bosons can occupy the same state, leading to phenomena like lasers, where countless photons act in unison. This division between fermions and bosons shapes the structure of matter and the behavior of forces. It is a fundamental organizing principle of the quantum world. The Pauli exclusion principle prevents electrons from collapsing into one another. Wolfgang Pauli discovered that no two electrons in an atom can have identical quantum numbers. This principle has vast consequences. It is why electrons arrange themselves in shells around the nucleus, each shell holding a limited number of electrons. Without the exclusion principle, all electrons would collapse into the lowest energy state, and atoms as we know them could not exist. Chemistry would be impossible. The principle arises from the quantum statistics of fermions. It is not a force pushing electrons apart, but a fundamental constraint on the possible states they can occupy. This constraint gives matter its volume and stability. It is why you do not fall through the floor and why solid objects resist compression. The exclusion principle is a quiet guardian of structure in the universe. Quantum chromodynamics describes the force that binds quarks together. Protons and neutrons are not fundamental. They are made of smaller particles called quarks, held together by the strong nuclear force. Quantum chromodynamics is the theory that describes this force. It is mediated by particles called gluons, which carry a type of charge called color, though it has nothing to do with actual colors. Quarks come in 6 types, or flavors, but only up quarks and down quarks form protons and neutrons. The strong force is peculiar. It grows stronger as quarks are pulled apart, making it impossible to isolate a single quark. This property, called confinement, ensures that quarks are always bound together in groups. Quantum chromodynamics is a cornerstone of the standard model of particle physics, explaining how the building blocks of matter interact at the deepest levels. Antimatter mirrors ordinary matter with opposite charge. For every particle, there exists an antiparticle with the same mass but opposite charge. The electron has a positively charged counterpart, called the positron. Protons have antiprotons. When a particle meets its antiparticle, they annihilate, converting their mass entirely into energy, usually in the form of photons. This process releases tremendous energy. As predicted by Einstein's equation, energy equals mass times the speed of light squared. Antimatter is not science fiction. It is produced in high-energy processes, such as cosmic ray collisions and particle accelerators. Positron emission tomography, or PET scans, used in medicine, relies on antimatter. The mystery is why the universe contains far more matter than antimatter. Shortly after the Big Bang, matter and antimatter should have been created in equal amounts, yet something caused a slight imbalance, allowing matter to dominate. This asymmetry is one of the great unsolved questions in physics. Virtual particles flicker in and out of existence in the vacuum. Even in empty space, quantum mechanics predicts constant activity. The uncertainty principle allows energy to fluctuate briefly, creating pairs of particles and antiparticles that appear and disappear in fractions of a second. These are called virtual particles. They are not directly observable, but their effects are measurable. Virtual particles contribute to phenomena like the Casimir effect, where two uncharged metal plates, placed close together in a vacuum, experience a tiny attractive force. This force arises because fewer virtual particles can exist between the plates than outside them, creating a pressure difference. Virtual particles also affect the energy levels of atoms, leading to subtle shifts in spectral lines called the Lamb shift. The quantum vacuum is not empty. It seethes with transient existence, a restless sea of potential. The Casimir effect demonstrates the reality of vacuum fluctuations. When two uncharged metal plates are placed extremely close together in a vacuum, they are pushed toward each other by a measurable force. This is the Casimir effect, predicted by quantum mechanics. It occurs because the vacuum is filled with virtual particles, constantly popping into and out of existence. Between the plates, only certain wavelengths of virtual particles can fit, while all wavelengths are present outside. This imbalance creates a net pressure, pushing the plates together. The effect is tiny, only noticeable at distances of nanometers, but it has been experimentally verified. It is a direct consequence of the quantum nature of empty space. The Casimir effect shows that even what we call a vacuum is rich with activity, governed by the ceaseless dance of quantum fluctuations. Hawking radiation causes black holes to slowly evaporate. Stephen Hawking applied quantum mechanics to black holes and made a startling discovery. Near the event horizon, the boundary beyond which nothing can escape, virtual particle pairs are constantly created. Normally, these pairs annihilate quickly. But near a black hole, one particle can fall in while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. To an outside observer, the black hole emits radiation, now called Hawking radiation. Over immense timescales, this process causes black holes to lose mass and eventually evaporate completely. The smaller a black hole, the faster it radiates. Tiny black holes, if they exist, would evaporate in bursts of energy. Hawking radiation links quantum mechanics, gravity, and thermodynamics in profound ways, suggesting that black holes are not eternal, but slowly fade, returning their mass to the universe as radiation. Quantum fields and forces. Quantum field theory describes particles as excitations in underlying fields. In modern physics, particles are not tiny billiard balls moving through empty space. They are ripples, or excitations, in quantum fields that permeate all of existence. Each type of particle corresponds to a field. The electron field fills the universe, and what we call an electron is a localized vibration in that field. Similarly, photons are excitations in the electromagnetic field. These fields are fundamental, more basic than the particles themselves. Quantum field theory unifies quantum mechanics and special relativity, providing the framework for understanding particle physics. It explains how particles are created and destroyed, how they interact, and why forces exist. Every interaction, every collision, every emission of light is a disturbance propagating through these invisible fields. Reality, at its deepest level, is a symphony of fields, each vibrating in its own way, creating the rich tapestry of matter and energy we observe. The electromagnetic force is mediated by photons. Forces in the quantum world are not pushes and pulls in the classical sense. They are exchanges of particles. The electromagnetic force, which binds electrons to nuclei and governs light, is mediated by photons. When two charged particles interact, they exchange virtual photons, carriers of the electromagnetic field. These virtual photons are not directly observable, but are essential to the mathematics of quantum electrodynamics, the theory describing electromagnetic interactions. The exchange of virtual photons creates the attraction between opposite charges and the repulsion between like charges. It is a strange picture. Forces arise from the constant exchange of particles flickering in and out of existence. Yet this framework predicts electromagnetic phenomena with astonishing precision, making quantum electrodynamics one of the most accurate theories in all of science. Quantum electrodynamics predicts phenomena to extraordinary precision. Quantum electrodynamics, or QED, describes how light and matter interact. It has been tested in countless experiments and consistently produces predictions that match observations to more than 10 decimal places. One famous example is the magnetic moment of the electron, a measure of how it responds to magnetic fields. QED predicts this value with such precision that the agreement between theory and experiment is one of the greatest triumphs of modern physics. The theory accounts for virtual particles, the self-interaction of electrons with their own electromagnetic fields, and a host of subtle effects. Developing QED required new mathematical techniques, including a method called renormalization to handle infinities that appeared in calculations. The success of QED demonstrated that quantum field theory could describe nature with unprecedented accuracy, laying the groundwork for the standard model of particle physics. The weak nuclear force governs radioactive decay. Some atomic nuclei are unstable, transforming into different elements by emitting particles and energy. This process, radioactive decay, is governed by the weak nuclear force. Unlike the electromagnetic force, which has infinite range, the weak force acts only over incredibly short distances, about 1/1000th the diameter of a proton. It is mediated by particles called W and Z bosons, which are much heavier than photons. The weak force allows neutrons to decay into protons, electrons, and neutrinos, a process essential for the fusion reactions in stars and the formation of elements. It is also responsible for certain types of particle interactions and plays a crucial role in the early universe. Though weak compared to electromagnetism and the strong force, the weak interaction is vital. Without it, stars would not shine, and the universe would be a very different place. Neutrinos are nearly massless particles that barely interact with matter. Neutrinos are among the most elusive particles in the universe. They have almost no mass and no electric charge, allowing them to pass through ordinary matter almost unimpeded. Trillions of neutrinos from the sun stream through your body every second, yet you never notice. They interact only through the weak nuclear force, making them incredibly difficult to detect. Neutrinos come in 3 types, or flavors, corresponding to the electron, muon, and tau particles. Experiments have shown that neutrinos can oscillate, changing from one flavor to another as they travel. This oscillation implies that neutrinos have a tiny but non-zero mass, a discovery that has profound implications for particle physics and cosmology. Neutrinos carry information from the cores of stars, supernovae, and even the Big Bang. Studying them opens a unique window into processes hidden from light. The strong nuclear force binds protons and neutrons in atomic nuclei. Protons in a nucleus are positively charged and repel each other electromagnetically. Yet nuclei hold together. The strong nuclear force overcomes this repulsion, binding protons and neutrons into stable configurations. It is the strongest of the 4 fundamental forces, but acts only over extremely short ranges, about the size of a nucleus. The strong force is mediated by gluons, which interact with quarks inside protons and neutrons. Unlike the electromagnetic force, which weakens with distance, The strong force remains constant, or even increases, as quarks are pulled apart. This property, confinement, prevents quarks from being isolated. The strong force is essential for the existence of atoms. Without it, nuclei would fly apart, and the elements that make up stars, planets, and life could not exist. Gluons carry the strong force and interact with themselves. Gluons are the carriers of the strong nuclear force, much as photons carry the electromagnetic force. But gluons have a unique property. They carry color charge, the type of charge that responds to the strong force. This means gluons can interact with each other, unlike photons, which do not interact with themselves. This self-interaction makes the strong force behave very differently from electromagnetism. It leads to confinement, ensuring quarks are always bound together, and to asymptotic freedom, where quarks interact more weakly at very short distances. The behavior of gluons is described by quantum chromodynamics, a theory that is mathematically complex but remarkably successful. Gluons are never observed in isolation, always hidden within protons, neutrons, and other particles. They are the glue holding matter together at its most fundamental level. The Higgs field gives particles their mass. In the 1960s, physicists realized that the Standard Model had a problem. According to the theory, particles like the W and Z bosons, which carry the weak force, should be massless, like photons. But experiments showed they have mass. To resolve this, Peter Higgs and others proposed the existence of a field permeating all of space, the Higgs field. Particles acquire mass by interacting with this field. The more strongly a particle interacts with the Higgs field, the more massive it is. Photons do not interact with the Higgs field at all, which is why they remain massless. The Higgs field is associated with a particle, the Higgs boson, which was discovered in 2012 at the Large Hadron Collider. This discovery confirmed a crucial piece of the Standard Model, explaining why particles have the masses they do. The Higgs boson was discovered in 2012 at CERN. For decades, the Higgs boson remained theoretical, predicted by the Standard Model, but not yet observed. Its discovery required building the Large Hadron Collider, the most powerful particle accelerator ever constructed. In 2012, scientists at CERN announced they had found a particle consistent with the Higgs boson. The discovery was a monumental achievement, confirming the mechanism by which particles acquire mass. The Higgs boson is unstable, decaying almost immediately into other particles. Detecting it required analyzing trillions of proton collisions and looking for subtle patterns in the debris. The discovery earned Peter Higgs and François Englert the Nobel Prize in Physics in 2013. It completed the Standard Model, a framework that describes all known particles and 3 of the 4 fundamental forces. Yet it also raises new questions about the nature of mass and the structure of the Higgs field itself. The Standard Model describes almost all known particles and forces. The Standard Model of particle physics is one of the great intellectual achievements of the 20th century. It catalogues the fundamental particles, the building blocks of matter, and describes 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. It classifies particles into 2 groups: fermions, which make up matter, and bosons, which carry forces. The model has been tested extensively and has passed every experimental challenge with remarkable precision. It explains a vast range of phenomena, from the stability of atoms to the behavior of particles in accelerators. Yet the Standard Model is incomplete. It does not include gravity, the 4th fundamental force. It does not account for dark matter or dark energy. It does not explain why neutrinos have mass or why there is more matter than antimatter in the universe. These gaps suggest that the Standard Model is part of a larger, more complete theory waiting to be discovered. Supersymmetry proposes a partner particle for every known particle. One extension of the Standard Model is supersymmetry, a theoretical framework that predicts a partner particle for every known particle. Each fermion would have a bosonic partner, and each boson a fermionic partner. These superpartners have not yet been observed, but if they exist, they could solve several mysteries. Supersymmetry could explain the nature of dark matter, provide a pathway to unifying forces, and resolve certain mathematical issues in particle physics. It also predicts that forces become equal in strength at very high energies, suggesting they are different manifestations of a single unified force. Despite extensive searches at particle accelerators, no superpartners have been found. If supersymmetry exists, the particles may be much heavier than current experiments can produce. The search continues, driven by the hope that nature's symmetry extends beyond what we have seen so far. Grand unification theories aim to merge forces into one. At everyday energies, the electromagnetic, weak, and strong forces appear distinct. But at extremely high energies, their strengths converge, hinting that they may be aspects of a single unified force. Grand unification theories attempt to describe this merger. They propose that in the early universe, moments after the Big Bang, these forces were indistinguishable, unified in a symmetric whole. As the universe cooled, the symmetry broke, and the forces separated into the distinct interactions we observe today. Grand unification predicts new phenomena, such as the decay of protons, though this has never been observed. The idea is elegant and compelling, suggesting that the complexity of nature's forces is an illusion arising from the low energies of our current environment. At its core, the universe may be simpler and more unified than it appears. Quantum mechanics and gravity remain incompatible theories. The greatest unsolved problem in fundamental physics is unifying quantum mechanics and general relativity. Quantum mechanics governs the small, describing particles and forces with extraordinary precision. General relativity governs the large, describing gravity as the curvature of space-time. Both theories are incredibly successful in their domains, yet they are fundamentally incompatible. General relativity is deterministic and smooth, treating space-time as a continuous fabric. Quantum mechanics is probabilistic and grainy, treating energy and matter as discrete. When physicists try to apply quantum mechanics to gravity, the equations produce nonsensical infinities. Numerous attempts have been made to reconcile them, including string theory, loop quantum gravity, and others. None have yet succeeded completely. The search for a theory of quantum gravity is one of the great quests of modern physics, promising to reveal the nature of space-time at the smallest scales and the behavior of the universe at its most extreme conditions. String theory proposes that particles are vibrating strings. One ambitious attempt to unify quantum mechanics and gravity is string theory. It suggests that the fundamental constituents of nature are not point-like particles but tiny, vibrating strings. Different modes of vibration correspond to different particles. An electron, a photon, a quark, all are different vibrations of the same underlying string. The theory requires extra dimensions beyond the familiar three of space and one of time. These extra dimensions are compactified, curled up so small they are undetectable at current energies. String theory naturally includes gravity, making it a candidate for a theory of everything. However, it is notoriously difficult to test. The energy scales at which strings would reveal their nature are far beyond what current accelerators can achieve. Critics argue that without testable predictions, string theory remains more mathematics than physics. Proponents counter that it provides a consistent framework for unifying forces and offers insights into black holes and the early universe. Loop quantum gravity attempts to quantize space-time itself. Another approach to quantum gravity is loop quantum gravity. Instead of treating space-time as smooth, it proposes that space-time itself is quantized, made of discrete loops woven together like a fabric. Space and time have a smallest possible scale, beyond which the concepts break down. This theory does not require extra dimensions or strings. It focuses on applying quantum mechanics directly to the geometry of space-time. Loop quantum gravity predicts that the Big Bang may have been preceded by a big bounce, where a previous contracting universe rebounded into expansion. It also suggests that black hole singularities, where general relativity predicts infinite densities, are replaced by finite, though extreme, conditions. Like string theory, loop quantum gravity faces challenges. It is mathematically complex and lacks clear experimental predictions. Yet it offers a different perspective on the nature of space and time, one where the fabric of reality is fundamentally quantum. The Planck scale is where quantum effects and gravity merge. At ordinary scales, quantum effects dominate the small, and gravity dominates the large. But at the Planck scale, distances of about 10 to the negative 35 meters, and energies far beyond anything achievable today, quantum mechanics and gravity become equally important. At this scale, space-time itself may become uncertain, fluctuating wildly. The smooth fabric of general relativity may dissolve into a quantum foam, a seething landscape where the familiar notions of distance and time lose meaning. The Planck scale marks the boundary of current physics, the frontier where our theories break down. Understanding what happens there requires a theory of quantum gravity. Though we cannot probe the Planck scale directly, studying its implications helps physicists explore the nature of reality at the most fundamental level. It is the edge of the known, where the universe's deepest secrets may hide. Quantum entanglement may be connected to the structure of space-time. Recent research suggests a deep link between quantum entanglement and the fabric of space-time. In general relativity, space-time is dynamic, curved by mass and energy. In quantum mechanics, entanglement creates correlations between particles. Some physicists propose that space-time itself emerges from entanglement. In this view, the connections between entangled particles weave together to form the geometry of space. Disrupting entanglement could change the structure of space-time. This idea, still speculative, hints at a profound unification. It suggests that space, time, and quantum mechanics are not separate but deeply intertwined. Space-time might not be fundamental, but an emergent property of quantum information. If true, this would revolutionize our understanding of reality. It would mean that the stage on which physics plays out is itself a quantum phenomenon, built from the relationships between particles. The universe, at its core, might be made not of matter or energy but of information and entanglement. Black holes may store information on their surfaces. When matter falls into a black hole, it seems to disappear, taking its information with it. But quantum mechanics suggests information cannot be destroyed. This paradox, the black hole information problem, has puzzled physicists for decades. One proposed solution is the holographic principle. It suggests that all the information inside a black hole is encoded on its two-dimensional surface, the event horizon. In a sense, the three-dimensional interior is a hologram projected from the surface. This idea extends beyond black holes, proposing that the entire universe might be a holographic projection. The information describing everything within a volume of space could be stored on its boundary. The holographic principle has deep implications for quantum gravity and the nature of reality. It suggests that dimensions, as we perceive them, may be an illusion, a way of organizing information that fundamentally exists in fewer dimensions. Quantum computers harness superposition and entanglement for computation. Classical computers process information using bits, each either 0 or 1. Quantum computers use qubits, which can be both 0 and 1 simultaneously, thanks to superposition. A quantum computer with a few dozen qubits can represent vastly more states than a classical computer with the same number of bits. Entanglement links qubits together, allowing operations on one to affect others instantaneously. This enables quantum computers to explore many possibilities at once, solving certain problems exponentially faster than classical machines. Tasks like factoring large numbers, simulating quantum systems, and searching databases could be transformed. However, building quantum computers is challenging. Qubits are fragile, easily disturbed by their environment, a problem called decoherence. Researchers are developing error correction techniques and stable qubit designs. Quantum computing is still in its early stages, but it promises to revolutionize fields from cryptography to drug discovery. Quantum cryptography offers theoretically unbreakable encryption. Traditional encryption relies on mathematical complexity. With enough computing power, codes can be broken. Quantum cryptography uses the principles of quantum mechanics to secure information in a fundamentally different way. One method, quantum key distribution, uses entangled photons to generate encryption keys. If an eavesdropper intercepts the photons, the act of measurement disturbs their quantum state, alerting the sender and receiver. The security comes not from mathematical difficulty, but from the laws of physics. Any attempt to intercept the key is detectable. Quantum cryptography has been demonstrated over fiber optic cables and even between satellites and ground stations. As quantum computers advance, they may threaten traditional encryption. Quantum cryptography offers a defense, ensuring secure communication in a quantum future. It is a practical application of quantum mechanics, turning the strangeness of the quantum world into a tool for privacy and security. Quantum teleportation transfers quantum states without moving particles. Quantum teleportation sounds like science fiction, but it is a real phenomenon demonstrated in laboratories. It does not transport matter or energy. Instead, it transfers the quantum state of one particle to another, even if they are far apart. The process relies on entanglement. Two particles are entangled and separated. The third particle, whose state you want to teleport, interacts with one of the entangled pair. This interaction is measured, and the measurement results are sent classically to the location of the other entangled particle. Using this information, the second particle's state is adjusted to match the original. The original particle loses its state in the process. It is not copied, but moved. Quantum teleportation has been achieved with photons, atoms, and even small clouds of particles. It is a key technology for future quantum networks, allowing the transfer of quantum information over long distances. Quantum sensors can measure fields and forces with unprecedented precision. Quantum mechanics not only underpins computation and communication, but also revolutionizes measurement. Quantum sensors exploit the sensitivity of quantum states to external influences. For example, atomic clocks use the precise energy levels of atoms to measure time with extraordinary accuracy. The best atomic clocks lose less than a second over billions of years. Quantum magnetometers detect magnetic fields with sensitivity far beyond classical devices, useful for medical imaging and mineral exploration. Quantum sensors can detect gravitational waves, probe the structure of molecules, and measure accelerations for navigation. These devices take advantage of superposition, entanglement, and interference to achieve precision that classical sensors cannot match. As quantum technology matures, quantum sensors promise to deepen our understanding of the world, revealing subtle signals and hidden structures in nature. Quantum mechanics explains the behavior of superconductors. At very low temperatures, certain materials lose all electrical resistance, becoming superconductors. Electric current flows through them without losing energy. This phenomenon is deeply quantum mechanical. In superconductors, electrons form pairs, called Cooper pairs, that move together in a coherent quantum state. This pairing is mediated by vibrations in the material's lattice, the arrangement of atoms. The paired electrons act like bosons, all occupying the same quantum state, allowing them to flow without scattering off impurities or defects. Superconductivity has practical applications, from powerful magnets in MRI machines to lossless power transmission. High-temperature superconductors, which work at less extreme cold, remain only partially understood. Unraveling their mysteries could lead to new technologies and deeper insights into quantum many-body systems, where countless particles interact in complex, collective ways. Superfluids flow without friction, defying classical physics. Helium, when cooled to near absolute zero, becomes a superfluid, a state of matter with bizarre properties. It flows without viscosity, climbing up the walls of containers and seeping through impossibly small cracks. Superfluidity, like superconductivity, is a quantum phenomenon. The helium atoms, which are bosons at these temperatures, condense into a single quantum state, moving collectively rather than as individual particles. This coherent behavior eliminates friction. The superfluid can flow forever without slowing down. It exhibits quantized vortices, whirlpools with discrete amounts of rotation. Superfluidity reveals the macroscopic consequences of quantum mechanics, where the behavior of countless atoms is governed by a single wave function. It is a state where quantum effects, usually confined to the microscopic, become visible in bulk matter, demonstrating the strangeness of the quantum world on scales we can see. Bose-Einstein condensates are clouds of atoms in the same quantum state. At extremely low temperatures, close to absolute zero, a gas of bosonic atoms can undergo a phase transition into a Bose-Einstein condensate. In this state, the atoms lose their individual identities and merge into a single quantum entity. They all occupy the same quantum state, behaving collectively as one coherent wave. The condensate is a macroscopic quantum object, large enough to see yet governed by the rules of quantum mechanics. Studying Bose-Einstein condensates allows physicists to explore quantum phenomena in controlled settings. They provide insights into superfluidity, quantum phase transitions, and the behavior of matter under extreme conditions. The first Bose-Einstein condensate was created in 1995, earning its creators the Nobel Prize. Since then, condensates have become valuable tools for probing the quantum world and testing fundamental theories. Quantum phase transitions occur without changes in temperature. Phase transitions are usually associated with temperature changes. Water freezes into ice when cooled. But quantum phase transitions occur at absolute zero, driven not by heat, but by quantum fluctuations. By varying parameters like magnetic field or pressure, a material can be tuned through a quantum critical point, where its properties change dramatically. Near these points, quantum effects dominate, and the system exhibits exotic behavior. Understanding quantum phase transitions is crucial for studying materials like high-temperature superconductors and topological insulators. It also connects to cosmology. The early universe underwent phase transitions as it cooled, shaping the structure of space and the formation of forces. Quantum phase transitions blur the line between the quantum and classical, revealing how quantum mechanics influences matter even in the absence of thermal energy. Topological insulators conduct electricity on their surfaces, but not inside. Topological insulators are materials with an unusual property. Their interiors are insulating, blocking electric current, but their surfaces conduct electricity, allowing electrons to flow without resistance. This behavior arises from the material's quantum mechanical properties and its topology, the mathematical study of shapes and surfaces. The surface states are protected by symmetry, making them robust against impurities and defects. Topological insulators are part of a broader class of materials with exotic quantum properties. They have potential applications in quantum computing, where their protected surface states could be used to create stable qubits. They also deepen our understanding of condensed matter physics, showing how quantum mechanics and topology combine to produce new states of matter. The discovery and study of topological insulators earned researchers the Nobel Prize in Physics in 2016. The quantum Zeno effect can freeze a system by continuous observation. In quantum mechanics, observation affects the system. The quantum Zeno effect takes this to an extreme. If a quantum system is observed continuously, it can be prevented from evolving. Imagine a particle in a superposition of two states. Normally, it oscillates between them. But if you measure the system repeatedly, each measurement collapses the wave function, resetting the oscillation. With frequent enough measurements, the particle never has time to transition, effectively freezing it in one state. This effect is named after Zeno's paradoxes, ancient philosophical puzzles about motion. The quantum Zeno effect has been demonstrated experimentally and has implications for controlling quantum systems. It shows how measurement is not passive, but an active tool that can shape the behavior of the quantum world. It also raises philosophical questions about the nature of time and change when observation is constant. Quantum mechanics challenges the notion of objective reality. Before quantum mechanics, it was assumed that objects have definite properties, independent of observation. A tree in a forest exists, even if no one sees it. Quantum mechanics complicates this. Particles do not have definite positions or momenta until measured. They exist in superpositions of possibilities. Some interpretations, like the Copenhagen interpretation, suggest that reality is created through observation. Others, like many worlds, propose that all possibilities are real. Experiments testing Bell's inequalities have shown that no local hidden variable theory can explain quantum correlations. This means that either reality is non-local, with instantaneous connections across space, or it lacks objective properties until measured. Quantum mechanics forces us to reconsider what we mean by reality, objectivity, and existence. It suggests that the universe is far stranger and more participatory than everyday experience would lead us to believe. Quantum applications and implications. Quantum mechanics enables the transistors that power modern electronics. Every computer, smartphone, and digital device relies on transistors, tiny switches that control the flow of electric current. Transistors are made from semiconductors, materials whose electrical properties are governed by quantum mechanics. In semiconductors, electrons occupy energy bands, ranges of allowed energies separated by gaps. By carefully adding impurities, a process called doping, engineers control how electrons move through the material. This quantum behavior allows transistors to switch on and off billions of times per second, processing information at incredible speeds. Without quantum mechanics, the transistor would not exist, and the digital age would never have arrived. The technology that shapes modern life, from the internet to medical devices, rests on the quantum behavior of electrons in semiconductors. It is a triumph of applying abstract theory to practical innovation. Lasers are coherent light sources based on quantum principles. Lasers produce light that is intense, focused, and coherent, with all photons moving in phase. The word laser stands for light amplification by stimulated emission of radiation, a process rooted in quantum mechanics. When an electron in an excited state drops to a lower energy level, it emits a photon. If that photon encounters another excited electron, it can stimulate the emission of a second photon, identical to the first, same frequency, phase, and direction. This cascading process amplifies light, producing a powerful, coherent beam. Lasers have countless applications, from cutting and welding to reading data on disks, from fiber optic communication to precision surgery. They also play roles in scientific research, enabling experiments that probe the quantum world. The laser is a direct application of quantum mechanics, transforming theoretical understanding into a versatile tool that shapes technology and industry. Magnetic resonance imaging uses quantum spin to see inside the body. MRI machines are a marvel of medical technology, providing detailed images of soft tissues without invasive procedures. They work by exploiting the quantum property of spin. Hydrogen nuclei, abundant in water and fat in the body, act like tiny magnets. When placed in a strong magnetic field, these nuclei align. A radio frequency pulse tips them out of alignment. As they relax back, they emit signals that are detected and used to construct images. The process is entirely quantum mechanical, relying on the interaction between nuclear spins and magnetic fields. MRI has revolutionized medicine, allowing doctors to diagnose conditions ranging from torn ligaments to brain tumors. It is a testament to how understanding the quantum behavior of atomic nuclei can lead to technologies that save lives and improve health. The invisible world of quantum spins becomes a window into the hidden structures of the human body. LEDs produce light through quantum transitions in semiconductors. Light-emitting diodes, or LEDs, are everywhere, from traffic lights to television screens. They are efficient, long-lasting, and produce light through quantum processes. An LED is a semiconductor device with two types of material, one with excess electrons and one with missing electrons, called holes. When electricity flows through the LED, electrons and holes meet at the junction and recombine. This recombination releases energy as a photon, a particle of light. The color of the light depends on the energy difference between the electron's initial and final states, which is determined by the material used. LEDs are direct applications of quantum mechanics, converting electrical energy into light with minimal waste heat. They have transformed lighting, reducing energy consumption and enabling new display technologies. The glow of an LED is the visible result of quantum transitions, electrons dropping between energy levels and illuminating the world. Solar cells convert light into electricity through the photoelectric effect. Solar panels capture sunlight and turn it into electrical power, a process that relies on the photoelectric effect, a quantum phenomenon. When photons from the sun strike a solar cell, they can transfer their energy to electrons in the material, typically silicon. If the photon has enough energy, it knocks the electron free, allowing it to flow as electric current. This is the same effect that Albert Einstein explained, and that earned him the Nobel Prize. Solar cells are designed to maximize this process, using layers of different materials to create electric fields that guide the freed electrons. As solar technology improves, it becomes more efficient, converting a larger fraction of sunlight into usable power. Solar energy is a quantum mechanical process at its heart, turning the quantum nature of light into a renewable source of energy for homes, businesses, and entire cities. Quantum mechanics explains the color and properties of materials. Why is gold gold-colored and silver silver? Why do some materials conduct electricity while others insulate? The answers lie in quantum mechanics. The arrangement of electrons in atoms and how they interact determines a material's properties. Metals have loosely bound electrons that move freely, conducting electricity and reflecting light, giving them their characteristic luster. Insulators have electrons tightly bound, unable to carry current. Semiconductors sit in between. The color of materials arises from how electrons absorb and emit light. When light strikes a material, electrons can jump to higher energy levels if the photon's energy matches the gap. The absorbed colors are missing from reflected light, giving the material its hue. Quantum mechanics explains why rubies are red, why the sky is blue, and why copper looks orange. The richness of the material world, its textures and colors, is a manifestation of quantum behavior in countless atoms. Chemical bonds form through the quantum behavior of electrons. Chemistry is the study of how atoms combine to form molecules. At its core, it is a quantum mechanical process. Chemical bonds arise when electrons from different atoms occupy shared or overlapping quantum states. In a covalent bond, electrons are shared between atoms, their wave functions overlapping to create a stable configuration. In an ionic bond, one atom donates an electron to another, and the resulting charged ions attract each other. The shapes of molecules, their stability, and their reactivity all depend on the quantum mechanics of electrons. The periodic table itself is a reflection of quantum principles, with elements grouped by the configuration of their electron shells. Without quantum mechanics, chemistry would be a collection of disconnected facts. Quantum theory provides the unifying framework, explaining why atoms bond the way they do and predicting the properties of new compounds before they are ever synthesized. Molecular orbitals describe how electrons are shared in molecules. When atoms come together to form molecules, their atomic orbitals, the regions where electrons are likely to be found, combine to form molecular orbitals. These new orbitals extend over the entire molecule, and electrons occupy them according to quantum rules. Bonding orbitals lower the energy of the system, stabilizing the molecule. Antibonding orbitals raise the energy and can weaken or prevent bonding. The arrangement of electrons in molecular orbitals determines the molecule's properties, its geometry, magnetism, and reactivity. Quantum chemistry uses these concepts to predict how molecules will behave, guiding the design of new drugs, materials, and catalysts. The intricate dance of electrons in molecules is a quantum ballet, choreographed by the principles of superposition, wave functions, and energy levels. Every breath you take, every taste, every scent, is mediated by the quantum mechanics of molecular orbitals. Quantum mechanics governs the rates of chemical reactions. Why do some reactions happen instantly, while others take years? The answer involves quantum mechanics and the concept of activation energy. For a reaction to occur, molecules must collide with enough energy to overcome a barrier, the energy needed to break old bonds and form new ones. The height of this barrier is determined by the quantum states of the molecules involved. Quantum tunneling can also play a role, allowing particles to pass through barriers they classically should not. In enzymes, nature's catalysts, quantum effects speed up reactions by lowering activation energies and positioning molecules precisely. Quantum mechanics also explains phenomena like isotope effects, where replacing an atom with a heavier isotope changes reaction rates. Understanding these quantum details allows chemists to design better catalysts, predict reaction pathways, and control processes in everything from industrial manufacturing to the metabolic pathways in living cells. Photosynthesis relies on quantum coherence in plants. Plants convert sunlight into chemical energy through photosynthesis, one of the most important processes on Earth. Recent research suggests that quantum mechanics plays a crucial role. When light is absorbed by a plant, the energy must travel from the light-harvesting molecules to the reaction center, where it is converted into chemical form. This transfer is remarkably efficient, close to 100%. Studies indicate that the energy moves as a quantum wave, exploring multiple pathways simultaneously through a phenomenon called quantum coherence. This allows the energy to find the most efficient route. The coherence lasts long enough, even in the warm, noisy environment of a living cell, to guide the energy. This discovery challenges the assumption that quantum effects are fragile and restricted to isolated systems. It suggests that nature has harnessed quantum mechanics to optimize processes essential for life, a beautiful intersection of quantum physics and biology. Quantum biology explores quantum effects in living systems. For decades, quantum mechanics was thought to be relevant only to physics and chemistry, with biological systems too warm and complex for quantum effects to persist. But quantum biology is emerging as a field, uncovering quantum phenomena in life. Beyond photosynthesis, evidence suggests that birds navigate using quantum entanglement in proteins in their eyes, sensing Earth's magnetic field. Enzymes may use quantum tunneling to speed up reactions. Even the sense of smell might involve quantum mechanics, with molecules distinguished by the vibrations of their bonds. These findings are still debated and researched, but they hint that life may exploit quantum mechanics in ways we are only beginning to understand. The boundary between the quantum and classical may be less sharp than imagined, with quantum effects woven into the fabric of biological processes, shaping the way organisms interact with their environment. Time crystals are phases of matter with repeating structures in time. Most crystals have repeating structures in space. Their atoms arrange in periodic patterns, like the orderly rows in a diamond. Time crystals, a recently discovered phase of matter, repeat in time. Their structure oscillates in a regular pattern, even without external energy input. This behavior seems to violate the laws of thermodynamics, which say systems should settle into equilibrium. But time crystals are driven by quantum mechanics. They exist in periodically driven systems, like atoms hit by laser pulses, and they enter a state that repeats at a different frequency than the driving force. Time crystals were first proposed theoretically, and then created in laboratories using trapped ions and other systems. They challenge conventional ideas about phases of matter and thermodynamics. While their practical applications are still unclear, they deepen our understanding of quantum many-body systems and the exotic states that quantum mechanics allows. Quantum entanglement may play a role in consciousness. Some researchers speculate that quantum mechanics might be involved in consciousness, the most mysterious aspect of human experience. One proposal, orchestrated objective reduction, suggests that quantum processes in microtubules, structures within neurons, contribute to consciousness. These microtubules could maintain quantum coherence, with wave function collapse corresponding to moments of conscious experience. The idea is controversial and not widely accepted. Most neuroscientists believe consciousness arises from classical processes in neural networks. The brain is warm, wet, and noisy, conditions that typically destroy quantum coherence quickly. Yet some argue that biological systems may have evolved mechanisms to protect quantum states. The connection between quantum mechanics and consciousness remains speculative, but it touches on profound questions. If consciousness does involve quantum processes, it would link the observer, a key figure in quantum mechanics, directly to the quantum world. It would mean that the mind, in some sense, is fundamentally quantum. The double-slit experiment has been performed with large molecules. The wave-particle duality of quantum mechanics is not limited to photons and electrons. Experiments have demonstrated it with increasingly large particles. In recent years, the double-slit experiment has been performed with molecules containing hundreds of atoms. These molecules, passing through two slits, produce interference patterns, showing they behave like waves. Yet when they hit the detector, they arrive as discrete particles. This pushes the boundary between the quantum and classical worlds. It shows that quantum superposition is not just a feature of the microscopic, but extends to objects approaching the scale of small biological molecules. The question of where quantum mechanics ends and classical physics begins remains open. As technology advances, experiments with even larger objects may reveal that the quantum nature of reality is more pervasive than we imagine, or they may finally define a clear transition to the classical world. Decoherence explains why macroscopic objects do not display quantum behavior. Quantum superposition and entanglement are rarely seen in everyday objects. Schrödinger's cat does not exist in a superposition of alive and dead. The reason is decoherence. When a quantum system interacts with its environment, the many particles in the surroundings become entangled with it. This entanglement spreads the quantum information across a vast number of particles, effectively erasing the coherence. The system appears to collapse into a definite state, even without an explicit measurement. For macroscopic objects, decoherence happens almost instantly. The interaction with air molecules, photons, and thermal vibrations destroys superpositions before they can be noticed. Decoherence is not a complete solution to the measurement problem, but it explains why the quantum world seems hidden from us. It shows that the classical world is an approximation, emerging from the quantum substrate when systems become entangled with their environments. Quantum mechanics suggests the universe may be fundamentally indeterminate. Before quantum mechanics, determinism was a cornerstone of physics. Given the initial conditions of a system, its future could be predicted with certainty. Quantum mechanics shattered this view. At the quantum level, outcomes are probabilistic. You can predict the likelihood of an event, but not which specific outcome will occur. This indeterminacy is not due to ignorance. It is built into the fabric of nature. Even with perfect knowledge of a quantum system, the future remains uncertain. This has profound philosophical implications. It suggests that the universe is not a clockwork mechanism, but a realm of possibilities. Some interpretations, like many worlds, restore determinism by saying all outcomes happen. Others embrace indeterminacy as fundamental. Either way, quantum mechanics challenges the idea of a predetermined universe, suggesting that chance and probability are woven into reality at its deepest level. Bell's theorem shows that no local hidden variable theory can explain quantum mechanics. In the 1960s, physicist John Bell derived a set of inequalities that any local hidden variable theory must satisfy. Such theories propose that particles have definite properties all along, hidden from us, and that influences cannot travel faster than light. Quantum mechanics predicts violations of Bell's inequalities. Experiments testing these predictions have consistently confirmed quantum mechanics. The results show that no theory based on local hidden variables can reproduce quantum correlations. Either the world is non-local, with instantaneous influences across space, or reality does not have definite properties until measured. Bell's theorem is one of the most profound results in physics. It rules out entire classes of theories and forces us to accept that the quantum world is fundamentally different from classical intuitions. It shows that the universe is more interconnected and stranger than common sense suggests. Experiments have closed loopholes confirming quantum non-locality. Early tests of Bell's inequalities left open certain loopholes, technical issues that could, in principle, allow local hidden variable theories to survive. Researchers have worked to close these loopholes through increasingly sophisticated experiments. Detection loopholes assume that the particles you detect are representative of all particles. Locality loopholes assume that the measurement settings are independent and that signals cannot travel between detectors during the experiment. In recent years, experiments have simultaneously closed all major loopholes, confirming quantum non-locality beyond reasonable doubt. These experiments use entangled photons, atoms, or superconducting circuits, with detectors separated by large distances. The results are unequivocal. Quantum mechanics is correct, and nature is non-local. These findings have practical implications, underpinning the security of quantum communication and the development of quantum technologies. They also deepen our understanding of reality, confirming that the quantum world is truly as strange as the equations suggest. Quantum mechanics is incompatible with naive realism. Naive realism is the belief that the world exists independently of observation, with objects possessing definite properties, whether we look at them or not. Quantum mechanics undermines this belief. Before measurement, particles do not have definite positions, momenta, or spins. They exist in superpositions, and only through interaction do definite outcomes emerge. Experiments violating Bell's inequalities show that properties cannot be predetermined and hidden. Reality at the quantum level is contextual, depending on what is measured and how. Some physicists and philosophers embrace this, viewing reality as relational, defined by interactions rather than intrinsic properties. Others find it unsettling, clinging to interpretations that try to preserve realism in some form. Quantum mechanics forces us to reconsider what we mean by existence and objectivity. It suggests that reality is not a collection of independent facts, but a web of relationships, a participatory universe where observers and observed are inseparably linked. The quantum measurement problem remains unsolved. When a quantum system is measured, it transitions from a superposition of states to a single outcome. But what constitutes a measurement? Where exactly does the quantum world end and the classical world begin? These questions form the measurement problem, one of the deepest puzzles in quantum mechanics. Different interpretations offer different answers. The Copenhagen interpretation says measurement collapses the wave function, but does not explain what qualifies as a measurement. Many worlds says there is no collapse. All outcomes happen in parallel branches. Consistent histories and decoherence approaches focus on how systems become effectively classical through environmental interaction. None of these solutions is universally accepted. The measurement problem touches on the nature of reality, the role of consciousness, and the limits of scientific explanation. It remains an open question, a reminder that despite quantum mechanics' success, our understanding of its foundations is incomplete. Quantum mechanics has inspired new philosophies of science. The development of quantum mechanics forced philosophers and scientists to rethink fundamental concepts. Before quantum mechanics, science aimed to describe an objective reality independent of observers. Quantum mechanics, with its probabilistic nature and observer dependence, challenged this goal. It inspired instrumentalism, the view that theories are tools for prediction rather than descriptions of reality. It fueled debates about realism, the existence of entities not directly observable. It raised questions about the nature of causality, with quantum events appearing uncaused. Philosophers of science have explored the implications, developing new frameworks to understand what scientific theories tell us about the world. Quantum mechanics also influenced broader philosophical thought, including discussions of free will, the nature of time, and the relationship between mind and matter. It is a theory that transcends physics, shaping how we think about knowledge, existence, and the limits of human understanding. Quantum mechanics and relativity are both fundamental yet incompatible. Two pillars support modern physics: quantum mechanics and general relativity. Quantum mechanics describes the small, the behavior of particles and forces at subatomic scales. General relativity describes the large, the curvature of space-time and the nature of gravity. Both theories are spectacularly successful in their domains, yet they are fundamentally incompatible. Quantum mechanics is probabilistic and discrete, treating space and time as a fixed background. General relativity is deterministic and continuous, treating space-time as a dynamic entity. Attempts to apply quantum mechanics to gravity produce infinities and inconsistencies. Physicists seek a theory of quantum gravity that unifies them. This quest drives research into string theory, loop quantum gravity, and other approaches. The incompatibility of quantum mechanics and relativity is a sign that our understanding is incomplete. Somewhere, there is a deeper theory, one that encompasses both the quantum and the gravitational, revealing the true nature of space, time, and matter. The search for quantum gravity may reveal the nature of time. One of the deepest mysteries in physics is the nature of time. In classical mechanics and relativity, time is a continuous parameter. In quantum mechanics, it is absolute and external. But in a theory of quantum gravity, time itself may be emergent, arising from more fundamental quantum processes. Some approaches suggest that time is not fundamental, but a useful approximation. At the Planck scale, the notion of time may break down, replaced by a timeless quantum state. The flow of time, the arrow pointing from past to future, might emerge from the increase of entropy, the second law of thermodynamics. Understanding time is crucial for unifying quantum mechanics and gravity. It touches on cosmology, the origin of the universe, and the ultimate fate of reality. Time may be an illusion, a construct of our perception, or it may be deeply real, woven into the fabric of the cosmos. The search for quantum gravity is, in part, a search for the true nature of time itself. Quantum field theory predicts the vacuum has infinite energy. In quantum field theory, even empty space is not truly empty. The vacuum is filled with fields, and quantum fluctuations give these fields energy. When you add up the energy of all these fluctuations across space, the result is infinite. This is the vacuum energy problem, or the cosmological constant problem. It is one of the biggest puzzles in physics. Observations show that the vacuum has a small but non-zero energy, dark energy, which drives the accelerated expansion of the universe. But quantum field theory predicts a value that is vastly larger, by a factor of 10 to the 120. This enormous discrepancy suggests something is deeply wrong or misunderstood. It could be that we are missing a mechanism that cancels most of the vacuum energy. It could be that our understanding of gravity or quantum mechanics is incomplete. Solving this problem may require a revolution in physics, connecting the quantum vacuum to the largest scales of cosmology. Dark matter may be made of particles yet to be discovered. Most of the matter in the universe is invisible, detectable only through its gravitational effects. This dark matter does not emit, absorb, or reflect light. It is not made of ordinary atoms. One leading candidate is that dark matter consists of new particles predicted by theories beyond the standard model. Weakly interacting massive particles, or WIMPs, are one possibility. These particles would interact through gravity and possibly the weak nuclear force, but not electromagnetism. Another candidate is the axion, a light particle proposed to solve a problem in quantum chromodynamics. Searches for dark matter involve sensitive detectors buried deep underground, shielded from cosmic rays, waiting to capture the rare interaction of a dark matter particle with ordinary matter. Despite decades of effort, dark matter particles have not been directly detected, yet the evidence for dark matter's existence is overwhelming. Its discovery could open a new chapter in particle physics, revealing a hidden sector of nature governed by quantum mechanics. Quantum fluctuations in the early universe seeded galaxies. The universe began in the Big Bang, a hot, dense state that expanded and cooled. In its earliest moments, quantum fluctuations, tiny random variations in energy, occurred everywhere. As the universe inflated, expanding exponentially, these quantum fluctuations were stretched to enormous scales. They became the seeds for the large-scale structure of the universe. Regions with slightly more energy attracted more matter, eventually collapsing to form galaxies, stars, and planets. The cosmic microwave background radiation, the afterglow of the Big Bang, carries the imprint of these fluctuations. Observations match predictions from quantum mechanics applied to the early universe with stunning precision. It is a profound connection. The galaxies, the stars, and ultimately life itself trace back to quantum fluctuations in the first fraction of a second. The quantum world shaped the cosmos, turning microscopic uncertainties into the vast structures we see today. The quantum universe. Inflation theory explains why the universe is so uniform. When we look at the cosmic microwave background, the radiation from the early universe, it appears remarkably uniform in all directions. This uniformity is puzzling. Distant regions of space, now separated by vast distances, could never have been in contact according to standard Big Bang cosmology. How did they come to have the same temperature? Inflation theory provides an answer. It proposes that the universe underwent a brief period of exponential expansion in its first moments, less than a trillionth of a second after the Big Bang. During inflation, a tiny region, small enough for its parts to reach equilibrium, was stretched to encompass the entire observable universe. This explains the uniformity. It also explains why space is so flat, and why we do not see magnetic monopoles or other exotic relics from the early universe. Inflation is driven by a quantum field, the inflaton field, and the quantum fluctuations in this field seeded the structure of the cosmos. The arrow of time may arise from quantum mechanics. Time has a direction. We remember the past but not the future. Eggs break but do not spontaneously reassemble. This arrow of time is tied to entropy, the measure of disorder, which always increases. But the laws of physics, both classical and quantum, are time-symmetric. They work the same, forward and backward. So why does time have a direction? One possibility involves the wave function collapse. Measurement breaks time symmetry, creating irreversible events. Another idea connects the arrow of time to the initial conditions of the universe. The Big Bang started in a low entropy state, and the universe has been increasing in entropy ever since. Quantum mechanics may play a role in setting these initial conditions or in the process of decoherence, which creates the appearance of irreversibility. The arrow of time remains one of the deepest mysteries, linking quantum mechanics, thermodynamics, and cosmology in ways we are still working to understand. Quantum immortality is a thought experiment in many worlds. In the many worlds interpretation, every quantum event splits reality into branches, each representing a different outcome. This leads to a strange thought experiment called quantum immortality. Imagine a setup where your survival depends on a quantum event, like the decay of a radioactive atom. In some branches, the atom decays, and you do not survive. In others, it does not, and you do. From your perspective, you will always find yourself in a branch where you survived. No matter how many times the experiment is repeated, you experience a form of subjective immortality. The thought experiment highlights the bizarre implications of many worlds. It raises questions about identity, probability, and the nature of consciousness. Most physicists do not take quantum immortality seriously as a real phenomenon, but it illustrates the strange terrain opened by quantum mechanics and its interpretations. It is a reminder that the theory forces us to confront ideas that stretch intuition to its limits. Quantum mechanics allows for quantum teleportation of information, not matter. Quantum teleportation has been demonstrated in laboratories, transferring the quantum state of particles across distances. But it is often misunderstood. Teleportation does not move matter or energy. It transfers information about a quantum state. The original particle loses the state being teleported. It is not copied, but moved. This process requires entanglement and classical communication. The information about how to reconstruct the state must be sent through conventional means, limited by the speed of light. So quantum teleportation does not enable faster-than-light communication, or the kind of teleportation seen in science fiction. However, it is a crucial technology for quantum computing and quantum networks. It allows quantum information to be transmitted over long distances without degradation. It shows that quantum information, the most fundamental kind, can be manipulated and transferred in ways that classical information cannot, opening new possibilities for communication and computation. The no-cloning theorem prevents copying quantum information perfectly. In classical computing, you can copy information as many times as you like, but quantum mechanics forbids this. The no-cloning theorem states that it is impossible to create an identical copy of an arbitrary, unknown quantum state. If you try to measure the state to copy it, the measurement collapses the wave function, destroying the original superposition. This is not a technological limitation, but a fundamental law of quantum mechanics. The no-cloning theorem has practical implications. It underpins the security of quantum cryptography. Any attempt to copy or intercept quantum information disturbs the system, revealing the intrusion. It also places limits on quantum computing and information processing. Yet it protects the uniqueness of quantum states, ensuring that quantum information is inherently different from classical information. The theorem is a reminder that the quantum world operates by rules that have no classical analog, rules that seem restrictive but enable entirely new possibilities. Quantum error correction is essential for building quantum computers. Quantum states are fragile. Decoherence, noise, and errors can destroy the delicate superpositions and entanglement that quantum computers rely on. Without error correction, quantum computations would quickly become useless. Quantum error correction addresses this by encoding information across multiple qubits. If one qubit is disturbed, the error can be detected and corrected without measuring the quantum state directly, which would collapse it. Developing effective error correction is one of the biggest challenges in building large-scale quantum computers. It requires additional qubits, sophisticated algorithms, and precise control over quantum systems. Progress is being made, with error-corrected qubits showing longer coherence times and more reliable operations. Quantum error correction is not just a practical necessity. It reveals deep connections between quantum information, coding theory, and the structure of quantum mechanics itself. It shows that even in a noisy, imperfect world, quantum information can be preserved and manipulated. Topological quantum computing uses exotic particles for stability. One approach to building stable quantum computers exploits topology, the mathematical study of shapes and their properties. Topological quantum computers would use anyons, exotic quasiparticles that exist in two-dimensional systems. Anyons are neither fermions nor bosons, but have fractional statistics. When anyons are braided around each other, their quantum state changes in ways determined by the topology of the braiding. This process encodes information robustly. Local disturbances cannot easily destroy it because the information is stored globally in the topology. Topological quantum computing is still largely theoretical, though experimental progress is being made in creating and manipulating anyons in certain materials. If successful, topological quantum computers could be far more stable than current designs, resistant to many sources of error. They represent a fusion of abstract mathematics and cutting-edge physics, using the structure of quantum mechanics in creative ways to overcome practical challenges. The holographic principle suggests reality is a projection. The holographic principle is one of the most mind-bending ideas in theoretical physics. It proposes that all the information contained in a volume of space can be encoded on the boundary of that space, like a hologram. This idea emerged from studying black holes, where information seems to be stored on the event horizon rather than inside. Some physicists believe the principle applies universally. Our three-dimensional reality might be a projection from a two-dimensional surface at the edge of the universe. This does not mean the universe is literally a hologram in the everyday sense, but that the true degrees of freedom, the fundamental bits of information, are fewer than we thought. The holographic principle has profound implications for quantum gravity, suggesting that space itself is emergent, arising from quantum information encoded on a boundary. It challenges our intuitions about dimensions, locality, and the nature of reality, pointing toward a deeper, stranger structure beneath the surface. Quantum entanglement and wormholes may be connected. Recent theoretical work suggests a surprising link between quantum entanglement and wormholes, hypothetical tunnels through space-time. In the mathematics of certain quantum systems, entangled particles behave as if connected by a wormhole. This idea, known as ER equals EPR, proposes that entanglement and wormholes are two descriptions of the same phenomenon. When two particles are entangled, they might be connected by a non-traversable wormhole in space-time. This connection is part of a broader effort to understand how space-time emerges from quantum mechanics. It suggests that the fabric of space is woven from entanglement, with geometry arising from quantum correlations. While highly speculative and far from proven, the idea illustrates how quantum mechanics and gravity may be deeply intertwined. It hints at a unified picture where the quantum and the geometric are not separate but different aspects of a single underlying reality. Quantum field theory describes the universe as a sea of interacting fields. In the deepest picture physicists have, the universe is not made of particles moving through empty space. It is a collection of quantum fields, each corresponding to a type of particle. These fields fill all of space. Excitations in the electron field appear as electrons. Ripples in the electromagnetic field are photons. Every particle is a localized disturbance in its associated field. These fields interact, exchanging energy and momentum, creating the rich dynamics of the physical world. Quantum field theory is the foundation of the Standard Model and the framework for understanding particles and forces. It is mathematically complex but conceptually elegant, unifying quantum mechanics and special relativity. It shows that matter and energy are not separate, but different manifestations of underlying fields. The universe, at its most fundamental, is a vibrating, interacting sea of quantum fields, with particles emerging as the ripples on this sea. Virtual particles mediate forces between particles. In quantum field theory, forces arise from the exchange of virtual particles. These particles are not real in the usual sense. They exist briefly, borrowing energy from the vacuum thanks to the uncertainty principle, and then disappearing. When two electrons repel each other, they exchange virtual photons. When quarks bind in a proton, they exchange virtual gluons. These exchanges create the forces we observe. Virtual particles are a bookkeeping device in the mathematics, but they correspond to real physical effects. They contribute to observable phenomena like the Lamb shift, the Casimir effect, and the anomalous magnetic moment of the electron. The concept of virtual particles reveals how forces work at the quantum level, not as continuous pushes or pulls, but as rapid exchanges of quanta, a ceaseless activity underlying the stability and interactions of matter. Renormalization makes sense of infinities in quantum field theory. When physicists first tried to calculate processes in quantum field theory, they encountered infinities. For example, the self-energy of an electron, arising from its interaction with its own electromagnetic field, appeared infinite. This was a crisis. The solution, developed by Feynman, Schwinger, Tomonaga, and others, is renormalization. It involves redefining quantities like mass and charge to absorb the infinities, making them finite and measurable. Renormalization is not just a mathematical trick. It reflects how we measure properties. We never observe bare parameters but effective ones, modified by quantum interactions. Renormalization has become a powerful tool, revealing the scale dependence of physical laws. The forces and particles we see at low energies differ from those at high energies. Renormalization allows physicists to make precise predictions and has been central to the success of quantum field theory, though it also raises philosophical questions about the nature of fundamental quantities. The hierarchy problem questions why gravity is so weak. Gravity is by far the weakest of the four fundamental forces. An electron and proton attract each other electromagnetically with a force far stronger than their gravitational pull. This weakness is puzzling. In quantum field theory, quantum corrections should make all forces similar in strength unless something prevents it. This is the hierarchy problem. Why is gravity so much weaker? One possibility is extra dimensions. Gravity might spread into additional spatial dimensions we do not perceive, diluting its strength in our three-dimensional world. Another idea is supersymmetry, which could stabilize the hierarchy through symmetry. The problem touches on the unification of forces and the nature of spacetime. Solving it could lead to breakthroughs in our understanding of gravity and quantum mechanics, potentially revealing new particles, dimensions, or principles. The hierarchy problem is a reminder that despite the success of our theories, deep puzzles remain. Supersymmetric particles have not been found yet. Supersymmetry predicts a partner for every particle in the Standard Model. These superpartners, if they exist, could solve several problems, including the hierarchy problem and the nature of dark matter. Physicists have searched for superpartners at particle accelerators, like the Large Hadron Collider, but none have been found. This does not disprove supersymmetry. The superpartners might be heavier than current experiments can produce, requiring even more powerful accelerators. Alternatively, supersymmetry might be broken in ways that make the particles less accessible. The lack of evidence has led some physicists to question whether supersymmetry is the right path, while others remain hopeful. The search continues. If superpartners are discovered, it would be a revolution, opening a new sector of physics and confirming ideas that have shaped theoretical work for decades. If not, it will push physicists to explore alternative theories, adapting to what nature reveals. Extra dimensions might exist beyond the three we perceive. Our everyday experience involves 3 dimensions of space and 1 of time. But some theories propose additional spatial dimensions, curled up so small we do not notice them. String theory requires extra dimensions, typically 6, beyond our familiar 3. These dimensions are compactified, folded into shapes much smaller than an atom. The geometry of these hidden dimensions determines the properties of particles and forces in our world. Other models suggest large extra dimensions, with gravity spreading into them and weakening in our 3-dimensional slice. If extra dimensions exist, they could be detected through their effects on gravity at short distances, or through the production of exotic particles at high energies. The idea of extra dimensions is speculative, but has driven much research. It shows how expanding our conception of space can address deep problems, linking quantum mechanics, gravity, and the structure of the universe. The multiverse concept arises from several areas of physics. The idea of a multiverse, a vast collection of universes beyond our own, appears in several contexts. In the many worlds interpretation, every quantum event creates branching universes. In eternal inflation, different regions of space stop inflating at different times, forming separate bubble universes with potentially different physical laws. String theory suggests a landscape of possible vacuum states, each corresponding to a universe with different properties. The multiverse is controversial. It is difficult, perhaps impossible, to test directly. Critics argue it strays from science into philosophy or metaphysics. Proponents say it arises naturally from well-motivated theories and helps explain fine-tuning, the apparent adjustment of physical constants to allow life. The multiverse challenges the notion of a single, unique universe, suggesting instead that ours is one among countless possibilities. Whether real or not, the concept expands our imagination and raises profound questions about existence, reality, and the scope of science. Quantum mechanics may explain the origin of the universe. One of the deepest questions is why there is something rather than nothing. Quantum mechanics offers a possible answer. In quantum cosmology, the universe itself is treated as a quantum system. The Big Bang might not be the absolute beginning, but a transition from a quantum state. Proposals like the Hartle-Hawking no-boundary model suggest the universe emerged from a state with no initial singularity, smoothly arising from a quantum wave function. In this view, time itself begins with the universe, and asking what came before is meaningless. Another idea is that the universe arose from a quantum fluctuation in a pre-existing quantum vacuum, a spontaneous event governed by probabilistic quantum laws. These ideas are highly speculative, pushing the limits of physics and mathematics. They suggest that the origin of the universe, the ultimate question, may be understood through quantum mechanics, the same framework that governs the smallest particles. The cosmos and the quantum may be one. The wave function of the universe is a concept in quantum cosmology. If quantum mechanics applies to everything, it should apply to the entire universe. This leads to the concept of a universal wave function, a quantum state describing all of reality. The Wheeler-DeWitt equation is an attempt to formulate this, a quantum equation for the cosmos. But applying quantum mechanics to the universe raises puzzles. What does it mean for the universe to be in a superposition? Who or what measures it? These questions blur the line between physics and philosophy. The universal wave function suggests that all possible histories of the universe coexist in superposition until something selects one. This something might be observers within the universe or the process of decoherence. The concept is speculative, but it pushes the boundaries of quantum mechanics, asking whether the framework applies not just to subsystems, but to the whole of existence. It is an attempt to understand the biggest system of all through the lens of quantum theory. Quantum mechanics has not been proven wrong in 100 years. Quantum mechanics was developed in the early 20th century, and since then, it has been tested in countless ways. Every experiment, from the behavior of atoms to the collisions of particles at the highest energies, has confirmed its predictions. No observation has contradicted quantum mechanics. Its success is unparalleled in the history of science. This does not mean the theory is complete. It does not include gravity. It leaves interpretational questions unanswered. But within its domain, quantum mechanics has never failed. This robustness suggests it captures something deeply true about nature. Whether it is the final word or part of a larger theory remains to be seen. But for now, quantum mechanics stands as one of humanity's greatest intellectual achievements, a framework that has revealed the hidden workings of reality and enabled technologies that shape modern life. Quantum entanglement has been verified across hundreds of kilometers. Experiments testing quantum entanglement have become increasingly sophisticated. Entangled photons have been sent through optical fibers and through the air across distances of hundreds of kilometers. Satellites have been used to distribute entangled particles between ground stations separated by vast distances. In every case, the correlations predicted by quantum mechanics are observed. The particles remain connected, their states linked instantaneously, regardless of separation. These experiments are not just tests of fundamental physics, they are steps toward building a quantum internet, a network where quantum information can be transmitted securely and efficiently across the globe. The ability to maintain entanglement over large distances is a technological triumph, showing that quantum effects, once confined to laboratories, can be harnessed in the real world. It is a testament to the enduring strangeness and power of quantum mechanics. Quantum simulation uses quantum systems to model other quantum systems. Some quantum systems are too complex to simulate on classical computers. The interactions of many particles, the behavior of exotic materials, the dynamics of quantum fields, all require computational resources that grow exponentially with system size. Quantum simulation offers a solution. By using one quantum system to mimic another, physicists can explore phenomena that are otherwise inaccessible. Ultra-cold atoms, trapped ions, and superconducting circuits have all been used as quantum simulators. These systems can be tuned to reproduce the behavior of condensed matter systems, high-energy physics, or cosmological scenarios. Quantum simulation is a bridge between theory and experiment, allowing researchers to test models, discover new phases of matter, and gain insights into fundamental processes. It leverages the quantum nature of matter to study the quantum world itself, using the universe's own rules to explore its mysteries. Quantum annealing is a technique for solving optimization problems. Optimization problems, finding the best solution among many possibilities, are central to fields from logistics to machine learning. Classical algorithms can struggle with complex optimization. Quantum annealing uses quantum mechanics to explore the solution space more efficiently. A quantum system is prepared in a superposition of all possible states, then slowly evolved so it settles into the lowest energy state, which corresponds to the optimal solution. Quantum tunneling allows the system to escape local minima, potentially finding better solutions than classical methods. Companies have built quantum annealers, devices designed specifically for this purpose. While not universal quantum computers, they show promise for certain problems. Quantum annealing is an example of using quantum mechanics not to simulate nature, but to solve practical problems, turning the quantum world's strange properties into computational power. Quantum machine learning explores algorithms that leverage quantum mechanics. Machine learning, the process of training algorithms to recognize patterns and make decisions, has transformed technology. Quantum machine learning investigates whether quantum computers can enhance these algorithms. Quantum systems can represent and process information in ways classical computers cannot. They might handle large datasets more efficiently, find patterns hidden in noise, or optimize models faster. The field is in its early stages, with researchers exploring quantum versions of neural networks, support vector machines, and other methods. Some quantum algorithms promise exponential speedups for specific tasks, though the extent of quantum advantage remains an open question. Quantum machine learning also faces challenges, including the difficulty of inputting and reading data, the need for error correction, and the scarcity of working quantum computers. Yet the potential is exciting. Combining quantum mechanics and machine learning could lead to breakthroughs in artificial intelligence, drug discovery, and understanding complex systems. Quantum supremacy refers to quantum computers outperforming classical ones. Quantum supremacy is the milestone where a quantum computer performs a task that no classical computer can complete in a reasonable time. In 2019, a quantum processor performed a calculation in minutes that would take classical supercomputers thousands of years. This achievement, while controversial and later improved upon by classical algorithms, marked a significant moment. It demonstrated that quantum computers can surpass classical ones for specific tasks. Quantum supremacy does not mean quantum computers are better at everything. For many problems, classical computers remain superior, but it shows that quantum computing is not just theoretical, it is real, practical, and advancing. Reaching supremacy is a stepping stone toward more powerful quantum computers that can solve useful problems in chemistry, materials, science, cryptography, and beyond. It is proof that harnessing quantum mechanics for computation is possible, and that a quantum revolution is underway. Quantum sensing could revolutionize measurements in science and industry. Quantum sensors exploit the sensitivity of quantum states to external influences, achieving precision far beyond classical devices. Atomic clocks, the most accurate timekeepers, use quantum transitions in atoms. Quantum magnetometers detect magnetic fields with extraordinary sensitivity, useful in brain imaging, mineral exploration, and fundamental physics. Quantum gravimeters measure gravitational fields precisely, aiding in underground mapping and testing general relativity. Quantum sensors could detect gravitational waves with greater sensitivity, probe the structure of molecules in living cells, or monitor environmental changes at unprecedented scales. As quantum technology matures, these sensors will move from laboratories into practical applications, transforming fields from medicine to geophysics. They are an example of quantum mechanics not only explaining the world, but providing tools to measure it more accurately, revealing details hidden from classical instruments. Quantum communication could enable perfectly secure networks. Classical communication is vulnerable. Messages can be intercepted and copied. Quantum communication, using the principles of quantum mechanics, offers a solution. Quantum key distribution allows two parties to share an encryption key with absolute security. Any attempt to intercept the key disturbs the quantum states, revealing the presence of an eavesdropper. The security is guaranteed by physics, not mathematical complexity. Experiments have demonstrated quantum communication over optical fibers and through satellites, establishing secure links across continents. Building a global quantum internet, where quantum information is transmitted and processed securely and efficiently, is a long-term goal. It would revolutionize communication, enabling applications from secure banking to private medical records. Quantum communication is one of the most mature quantum technologies, already transitioning from research to practical deployment, showing that the quantum future is not distant speculation, but an emerging reality. Reflections on the quantum world. Quantum mechanics reveals a universe far stranger than imagination. When you first encounter quantum mechanics, it feels impossible. Particles in two places at once. Influences traveling instantaneously across space. Outcomes determined by probability rather than certainty. It defies everything we learn from everyday experience. Yet it is true. Every experiment confirms it. Quantum mechanics is not a flawed approximation but an accurate description of how nature works at its smallest scales. The strangeness is not a bug but a feature, revealing that the universe is richer, more mysterious, and more interconnected than we could have guessed. What feels impossible is simply unfamiliar. The quantum world operates by different rules, and once you accept them, a new understanding emerges. Reality is not what it seems. Beneath the surface of ordinary experience lies a realm where particles dance in superposition, where observation shapes existence, and where the very fabric of space and time may be woven from quantum threads. Every technology of the modern age relies on quantum principles. Look around you. The device you are using to read this, the lights illuminating your room, the medical technologies that save lives, all depend on quantum mechanics. Transistors, the building blocks of computers and smartphones, work because of the quantum behavior of electrons in semiconductors. LEDs and lasers exploit quantum transitions. MRI machines use the quantum spin of nuclei. Solar panels convert light into electricity through the photoelectric effect. GPS satellites rely on atomic clocks that use quantum mechanics to measure time with incredible precision. Without quantum mechanics, the modern world would not exist. The theory that seems abstract and remote is, in fact, the foundation of technology, shaping daily life in countless ways. Every time you use a computer, turn on a light, or benefit from modern medicine, you are interacting with the quantum world. It is not distant, it is here, woven into the fabric of civilization. Quantum mechanics forces us to rethink the nature of reality. Before quantum mechanics, the world seemed straightforward. Objects had definite properties, independent of observation. Cause and effect followed clear rules. But quantum mechanics challenges all of this. It suggests that properties do not exist until measured. It shows that events can be probabilistic without clear causes. It reveals non-local connections, where distant particles remain correlated instantaneously. These findings are not merely technical details. They are profound statements about the nature of reality. They force us to reconsider what it means for something to exist, what it means to know, and what it means to observe. Philosophers, scientists, and thinkers have grappled with these questions for a century. Some embrace the strangeness, finding beauty in a universe that defies simple description. Others search for deeper theories that restore clarity. Either way, quantum mechanics has expanded our understanding, showing that reality is far more subtle and complex than common sense suggests. The quantum world is both hidden and everywhere. Quantum effects seem invisible in daily life. We do not see superpositions or notice entanglement. Yet the quantum world is not separate. It is the foundation. Atoms, the building blocks of everything, are quantum objects. Their stability, the way they bond, the colors they produce, all arise from quantum mechanics. The light you see is made of photons, quantum particles. The solidity of matter comes from the Pauli exclusion principle, a quantum rule. The quantum world is hidden only because we experience its averaged, macroscopic effects. We see the statistical outcomes, not the underlying quantum dance. But it is always there, beneath the surface, governing the interactions that create the world we perceive. Understanding quantum mechanics is like gaining X-ray vision into reality, seeing the hidden processes that sustain existence. The quantum is not elsewhere. It is here, now, in every atom, every photon, every moment. Quantum mechanics unites the very small and the very large. At first, quantum mechanics seems confined to the microscopic, but its influence reaches to the cosmos. Quantum fluctuations in the early universe seeded the formation of galaxies. Stars shine because of quantum tunneling in nuclear fusion. The matter we are made of was forged in the quantum processes of supernovae. Black holes, the most extreme gravitational objects, exhibit quantum behavior through Hawking radiation. Even space-time itself may be a quantum phenomenon, emerging from entanglement. The quantum and the cosmic are not separate, but intertwined. The smallest scales shape the largest structures. The universe, in all its vastness, bears the imprint of quantum mechanics. To study the quantum is to study the universe. To understand the cosmos is to understand quantum physics. They are two facets of a single, interconnected reality, where the infinitesimal and the infinite reflect each other. The mysteries of quantum mechanics inspire awe and humility. Despite a century of study, quantum mechanics remains mysterious. We have equations that work, experiments that confirm them, and technologies that exploit them. But the deeper questions linger. What is the wave function? What happens during measurement? Is reality fundamentally probabilistic or deterministic? Are there hidden layers we have not discovered? These mysteries are not failures. They are invitations. They remind us that the universe is vast, our knowledge incomplete, and there is always more to learn. The mysteries of quantum mechanics inspire humility. They show that nature is subtler than our theories, more surprising than our expectations. They also inspire awe. To confront the quantum world is to encounter beauty and strangeness intertwined, a reality that exceeds imagination, yet reveals itself through careful observation and thought. The mysteries are part of the journey, guiding us deeper into understanding. Quantum mechanics bridges science and philosophy. Quantum mechanics is not just physics. It touches on philosophy, raising questions about knowledge, reality, and existence. Can we know something if measuring it changes it? Does reality exist independently of observers? What is the relationship between information and physical states? These are philosophical questions, yet they arise directly from quantum mechanics. The theory forces scientists and philosophers to work together, exploring the implications of a framework that defies classical intuition. Some view quantum mechanics instrumentally, as a tool for prediction without deeper meaning. Others see it as revealing profound truths about the universe. The debate continues, enriching both fields. Quantum mechanics shows that science and philosophy are not separate but interwoven. The deepest scientific theories raise the deepest philosophical questions. To study quantum mechanics is to engage with the nature of existence itself. The quantum world is a realm of infinite possibility. In the quantum realm, before measurement, systems exist in superpositions, holding multiple possibilities at once. This is not uncertainty about which state is real. All states are real in some sense, existing together as potential. Measurement collapses this superposition, selecting one outcome. But until that moment, the quantum world is open, a landscape of possibilities, where the future is not yet written. This openness is fundamental. It means the universe is not predetermined but unfolding, with each interaction shaping what comes next. The quantum world is creative, generating new outcomes, new states, new realities. It is a reminder that the universe is not a static structure, but a dynamic process, where possibility and actuality intertwine. In the quantum realm, the future is not fixed. It is probabilistic, waiting to be realized through interaction and observation. Every moment is a choice, a collapse, a crystallization of possibility into reality. Quantum mechanics shows that nature is irreducibly interconnected. In classical physics, objects are separate, interacting through forces but fundamentally independent. Quantum mechanics reveals a different picture. Entanglement links particles across space. Measurement of one affects the other instantly. The quantum state of a system cannot be decomposed into independent parts. The whole is more than the sum. This interconnectedness is fundamental. It suggests that separation is an illusion, a useful approximation, but not the deepest truth. At the quantum level, the universe is a web of relationships, where every part is connected to every other. This interconnectedness extends beyond particles. It may include space and time, with geometry emerging from entanglement. It hints at a holistic view of reality, where the divisions we perceive are constructs, and the underlying nature is unified, continuous, and whole. Quantum mechanics shows that isolation is impossible. Everything is part of a larger whole, bound together in ways we are only beginning to understand. Quantum mechanics suggests the observer is part of the system. In classical physics, the observer stands outside, watching without influence. Quantum mechanics erases this boundary. The observer and the observed are intertwined. Measurement affects the system. The act of observation collapses the wave function, bringing properties into existence. This does not necessarily mean consciousness is required, but it does mean that interaction, observation, and measurement are integral to the physical process. The observer is not separate, but part of the system, shaping outcomes through participation. This participatory nature has deep implications. It suggests that reality is not a passive backdrop, but a co-creation, emerging through the interaction of systems. It challenges the idea of objectivity, showing that what we observe depends on how we observe it. The observer is woven into the fabric of the quantum world, a participant in the unfolding of reality. The quantum world invites us to embrace uncertainty. Uncertainty is often seen as a limitation, a lack of knowledge. But in quantum mechanics, uncertainty is fundamental. The Heisenberg uncertainty principle shows that certain pairs of properties cannot both be known precisely. This is not ignorance, but a feature of nature. The universe has intrinsic limits to precision. Embracing this uncertainty is liberating. It means the world is not rigidly determined, but open, flexible, and creative. It means there is room for spontaneity, for the new, for the unexpected. Uncertainty is not a flaw, but a source of richness. It allows for the diversity of outcomes, the variety of experiences, the unfolding of possibilities. In the quantum world, uncertainty is not something to overcome, but something to accept. It is part of the beauty, the mystery, the wonder of existence. To embrace uncertainty is to embrace the quantum nature of reality, where the unknown is not a void, but a field of potential. Quantum mechanics is a story still being written. The development of quantum mechanics is not finished. New experiments probe its foundations. New technologies harness its principles. New interpretations offer fresh perspectives. The search for quantum gravity continues, aiming to unify quantum mechanics with general relativity. Quantum computing is advancing, promising to revolutionize information processing. Quantum biology explores whether quantum effects play roles in life. The field is dynamic, evolving, full of open questions and opportunities. Every generation of physicists adds to the story, discovering new phenomena, refining theories, pushing boundaries. Quantum mechanics, despite its century-long history, remains a frontier. It is a living theory, growing and adapting as we learn more. The story is far from over. Each new discovery adds a chapter, deepening our understanding and raising new mysteries. To study quantum mechanics is to join an ongoing adventure, a collective effort to unravel the deepest secrets of nature. The quantum realm is a place of profound beauty. There is beauty in the mathematics of quantum mechanics. The equations, elegant and symmetric, describe the behavior of particles with precision. There is beauty in the experiments, where abstract concepts become tangible, where entanglement is created and measured, where interference patterns emerge. There is beauty in the implications, the strange, counterintuitive truths that challenge and expand our understanding. The quantum world, with its superpositions, its probabilities, its non-local connections, is not just puzzling, it is beautiful. It reveals a universe far richer and more intricate than appearances suggest. The beauty is not superficial, it is deep, rooted in the structure of reality. To appreciate quantum mechanics is to see the elegance in nature's design, the harmony in its laws, the subtlety in its workings. It is to find wonder in the invisible, the microscopic, the hidden processes that sustain existence. The quantum realm is a testament to the beauty of the cosmos. Quantum mechanics teaches us that reality is more than we perceive. Our senses evolved to navigate the macroscopic world. They do not reveal quantum effects. We see objects as solid, isolated, deterministic. But this is an approximation. The reality beneath is quantum, probabilistic, interconnected, strange. Quantum mechanics teaches us that perception is limited. What we see is a fraction of what exists. Atoms are mostly empty space, yet matter feels solid because of quantum forces. Light is both wave and particle, yet we experience it as continuous. Entanglement links distant particles, yet we perceive them as separate. Reality is richer than perception. It extends beyond the reach of our senses into realms revealed only through experiment and mathematics. To learn quantum mechanics is to expand awareness, to see beyond appearances, to glimpse the deeper structure of the universe. It is a reminder that there is always more, that the world is larger, stranger, and more wonderful than we imagine. The quantum world is a place where opposites coexist. Quantum mechanics is full of dualities. Particles are also waves. Measurement creates reality, yet disturbs it. Deterministic equations produce probabilistic outcomes. Local interactions lead to non-local correlations. These are not contradictions but complementary aspects. The quantum world does not fit into binary categories. It transcends them, holding opposites together in a coherent whole. This coexistence of opposites is a feature, not a flaw. It reflects the richness of nature, which cannot be reduced to simple either or distinctions. The quantum world teaches us to think in new ways, to accept paradoxes, to hold multiple perspectives simultaneously. It challenges rigid thinking, inviting flexibility and openness. In the quantum realm, opposites are not enemies but partners, two sides of a deeper unity. The ability to embrace this duality is key to understanding quantum mechanics and perhaps, to understanding reality itself. Quantum mechanics is a testament to human curiosity and ingenuity. The development of quantum mechanics is one of humanity's greatest achievements. It required breaking free from centuries of classical thinking, questioning assumptions, and embracing ideas that seemed absurd. Physicists built new mathematical tools, designed ingenious experiments, and persisted through confusion and controversy. The result is a theory of extraordinary power and precision, one that describes nature at its most fundamental level. Quantum mechanics is a testament to what humans can achieve through curiosity, creativity, and collaboration. It shows that even the strangest aspects of reality can be understood, given enough effort and imagination. It is also a reminder that knowledge is a collective endeavor. Quantum mechanics was not the work of a single genius, but the contribution of many minds, building on each other's insights. It is a monument to the human spirit, our drive to explore, to question, to understand the universe we inhabit. The quantum world is waiting to be explored. Despite all we have learned, quantum mechanics remains a frontier. There are mysteries to solve, technologies to build, and implications to uncover. The search for quantum gravity continues, aiming to unite quantum mechanics and general relativity into a single framework. Quantum computers are in their infancy, with potential we are only beginning to tap. Quantum biology may reveal new principles of life. The foundations of quantum mechanics, the interpretations, the measurement problem, remain debated. Each of these is an invitation. The quantum world is not fully known. It is waiting for new ideas, new experiments, new minds to push the boundaries. Whether you are a student, a researcher, or simply curious, the quantum realm offers endless opportunities for discovery. It is a landscape of questions, where every answer opens new horizons. The exploration is ongoing, and the next breakthrough could come from anyone willing to ask, to imagine, to venture into the unknown. Quantum mechanics is a mirror reflecting the universe's deepest nature. When we study quantum mechanics, we are not just learning about particles and waves. We are learning about the universe itself. The theory reveals patterns, symmetries, and principles that appear everywhere. The probabilistic nature of quantum mechanics mirrors the openness of the cosmos. The non-locality reflects the interconnectedness of all things. The role of the observer hints at the participatory nature of reality. Quantum mechanics is a mirror, showing us the universe's structure, its beauty, its strangeness. It is also a mirror for humanity. In developing quantum mechanics, we see our capacity for abstraction, creativity, and persistence. In grappling with its mysteries, we confront our limits and our potential. The quantum world is not separate from us. It is part of the same reality we inhabit, the same universe we are trying to understand. To study quantum mechanics is to study ourselves, our place in the cosmos, and the nature of existence itself. Every particle, every interaction, every moment is governed by quantum mechanics. From the smallest electron to the largest star, from the briefest instant to the age of the universe, quantum mechanics is at work. It governs how atoms bond, how light propagates, how stars shine. It shapes the chemistry of life, the flow of energy, the structure of space and time. Quantum mechanics is not a niche theory for exotic phenomena. It is the foundation of all physical processes. Every moment of your existence, every breath, every heartbeat, is sustained by quantum interactions. The proteins in your cells, the neurons in your brain, the light entering your eyes, all depend on the quantum behavior of particles. The universe is quantum, through and through. To understand quantum mechanics, is to understand the rules by which everything happens, the laws that govern every event, every change, every transformation. It is the grammar of nature, the language in which the cosmos expresses itself. Closing thoughts. And so, dear listener, our journey through the quantum realm comes to a close. From the strange dance of particles in superposition to the distant connections of entanglement. From the building of atoms to the birth of galaxies, we have wandered together through a universe far stranger and more beautiful than everyday experience reveals. We have glimpsed the quantum foundations of reality, the probabilistic nature of existence, and the deep interconnections that bind everything together. The quantum world reminds us that the universe is not a machine, but a living, evolving, participatory tapestry, where observation shapes outcomes, where uncertainty creates possibility, and where the smallest scales influence the largest structures. As you lie here, letting your thoughts slow and your breath deepen, imagine yourself drifting into the quantum realm. Picture particles flickering in and out of existence, waves of probability spreading through space, entangled photons connected across vast distances. See the delicate superpositions, the interference patterns, the gentle glow of atoms transitioning between energy levels. All of it flowing into stillness, into silence, into the quiet, where quantum and classical merge, where the observer and the observed become one. The quantum world has carried us through a century of discovery, and it will carry countless generations more. Its story is not finished, and in exploring it, neither is ours. Just as particles settle into their lowest energy states, every waking thought drifts gently into rest. The mysteries remain, patient and waiting, while you slip into the quantum superposition between waking and dreaming. If you happen to still be awake, you can continue your explorations another time, but if your eyes are growing heavy, let the gentle uncertainty of the quantum world hold you. Let the waves of probability carry you softly into sleep, into stillness, into the vast and timeless silence, where even quantum fluctuations find rest. Close your eyes, breathe deeply, and drift into sleep, into peace, into the quiet hum of the quantum cosmos watching over you. Good night.